All right, let's go ahead and get started. Welcome everyone to lecture 4. This is like the end of week 2 over IAP. IAP is 4 weeks long. We're halfway there. Congratulations. You've been doing like 2 weeks of solid PCB work, and the class hasn't caught on fire yet. So we're pretty proud of that. Cool. So today, we're going to talk a lot about the Bluetooth speaker design. We're basically going to do a walkthrough of that and basically use that as a case study for like how you do good layout and also just how the thing works. Because the purpose of this lecture is to give you the same context for track 1 people as to like how your circuitry works as we gave for the track 2 people with the motors lecture last week. So I want to give you context because on next week we're going to be actually putting boards together, and those boards are not going to work right the first time once you put them together. So you have to do some debugging. It's really, we'll talk about debugging as a lecture next week, but it's really hard to try and figure out what's wrong with your circuit when you don't know how it works. So the purpose of today is to like build some intuition for like how things work together. And so that you have a functional enough understanding of what's going on to the point where when stuff breaks, you can start probing around and working on it yourself. Cool. OK, but first we have a couple announcements. The first being Lab 2 DRs should mostly be done by now. If we did not DR your schematic and you need it or want it DR'd, please contact us, like either email or make a Piazza post. We basically just want to make sure that everybody has schematics that look good and are error-free as they start heading into layout with Lab 4. So speaking of Lab 4, it is out. It is due next Thursday, a week from yesterday. This is going to take you a while. It's like 10 to 15 hours worth of work to get a good layout. Please like put effort into your layout. If you drag all of your components over like onto the board and then just like haphazardly throw them down, push the auto route button, it's going to look bad. And we're not going to be able to give you any feedback on how to make your circuit better, how to improve your layout, because we would just be telling you things that we have already told you and things you already know. Keeping components tightly together, packed tightly together, spending a lot of time on good placement, and then also just optimizing your layout and routing things properly. We don't want to have to tell you things that you already know, so please just like work on this. And laying out the entire board is actually a pretty daunting task. However, it's the reason why we're able to give you academic credit here. And also, the best way to learn how to do this is just by doing it. And this is like a good starter project. It's a system of moderate complexity, and we'll be diving into that complexity in a bit. And yeah, we're just excited to see what you come up with.
Just briefly, because it's not mentioned in the lab instructions, I think no one should be able to access it anymore, but if you have somehow found access to our PCB layout by any means, please do not use it. If you use it, we will be forced to fail you. We're taking the class for credit. The point is for you to do it on your own so that we can design review you, so that we can show you what the layout is supposed to look like. So don't use our layout as your layout. Also, there are issues with our layout. Our layout is not perfect, so it's best if you learn by doing it yourself. And then, at least the way I learned PCB layout is I did something bad and then I got yelled at profusely by a bunch of people who were older than me and much smarter than me. And it's a very good technique for learning. We won't go too far, we promise, but try to do something first.
Yep. Just to echo that, like we are very good at detecting our own layout. So if you copy paste things from stuff that we've already done, like we'll notice. And that's not pedagogically useful to you, so just don't. You're going to see some examples of our layout next week, like Tuesday, when you start actually putting stuff together. So you'll get an idea of like one possible solution to the Bluetooth speaker. It is not the perfect one. There's some things that we could have done better. There's some things we could have done worse. If you like go in assuming that like that layout is perfect ground truth and you should copy it, you will not learn a lot, and you will make something that has mistakes in it. But they will be our mistakes, not yours. So, cool. So Lab 4 is out. We're also going to be starting Lab 5 Tuesday, which is assembling everything. This is going to be the last lab that we do together, but it's going to span multiple days. So it's going to take us a long time to put our Bluetooth speakers together. There's a lot of parts on there. There's a lot of work we have to do in order to get it properly assembled. That's going to take you a while, more than a 2-hour lab section. So it's going to be a multi-day lab, but it's the last thing that you will do in lab. That's what we're going to be spending all of next week on, is assembling the speakers, and then after that we will start like debugging them, trying to get them working for y'all. Cool. We also have a lab feedback form on Piazza. I chunked it up there last night. But basically, if you have opinions on how the labs went, or if there's anything you'd like to see be different, or something that you liked and you want to tell us about, go ahead and fill those out. Literally, the only required question on there is like what lab you're talking about. So like if you have any thoughts whatsoever, just chunk them up there. We read them all, and like if we can incorporate your feedback like immediately, we will. Or if it's something that gets rolled in next year, that's like going to be on our horizon too. So we listen to you. Fundamentally, this class is again for y'all. So tell us how we can do the best job at giving you that. Cool. And then if you're track 2, we're going to do DRs next week, and the scheduling for that is going to go live after lecture. I got to put together a like a doodle poll for things. We should have a lot of availability next week. It's going to be mostly like Monday, Wednesday, Friday after lecture, going into the evening. And I'll talk more about like what goes into those DRs in a second. But if that does not work for you or your scheduling needs, please contact us. The sooner the better. We can like try and play some scheduling Tetris a bit in order to get you a spot that works. Cool. And as far as what goes into a DR, fundamentally the purpose of this is to convince us that you know what you're doing, which is vague, but here's how that's going to look. We're going to ask you to make some slides or some kind of design document, something that you can present and tell us how your system is going to work. We're going to ask you to aim for like 15 minutes of you talking about your design, and then 15 minutes of Q&A with us, where we ask you about it and try and resolve any questions that we've got. And loosely, this should include telling us what problem you're trying to solve. So like if you are trying to make a motor controller, you should tell us that, OK, I am trying to make something that can drive this particular kind of motor in this particular kind of way from this kind of source. So tell us what you're trying to do, and then tell us how you're going to do it. With like some circuit topology, let's say you're using like a 6-transistor inverter for that, you should tell us. Or if you're using some other circuit that like, if you're using something else, tell us about that as well. Walk us through like the quick SparkNotes version of the theory of what you're trying to implement, just so that we know that like when you put this together and it doesn't work, you're going to be able to debug it and like and understand how it works on the inside. Cool. If there's any other circuit options you had when designing this, let's say you're making a guitar amplifier, there's like a bajillion kinds of amplifiers. Tell us about the one you picked, why you picked it, why the other ones were bad. Let's not spend too much time on like the nitty-gritty of what. Sorry. OK, cool. Sorry. Yeah, show us how the circuit that you've chosen to implement works. Don't spend a ton of time on like the other ones, because we're mostly concerned with what you think is best. And cool. And then walk us through what concerns that raises for PCB design. Like if you have some amplifier that's running at audio frequency, like we're about to talk about today, there's some like pretty nuanced stuff that you have to take care of in order to make sure that your audio sounds good and it's not like a potato. So tell us how you resolve those. And if it is not something that is covered in the class or that we've talked about before, go ahead and like throw in a reference or two that tells us that you know an authoritative source that says that that'll fix the problem. So for instance, let's say that you are making, we'll use a motor controller again as an example. Let's say you're making a motor controller and you know about how much power you're going to be dissipating in your transistors. You need to convince us that you're going to be able to get that out of the transistor and not blow it up. So that means if you're using like thermal vias, tell us like how much power you anticipate to like pull through those, and tell us where those numbers come from. If you're using like heat sinks and whatnot, walk us through like the thermals for that, and things of that nature. Again, doesn't have to be like incredibly like rigorous. We just want to see that like, yes, this solution is based in reality and we know that it can work. Today's lecture is going to have a lot of these concepts, actually. We're basically going to be like giving something of like an extended DR on the Bluetooth speaker. And so you'll see a lot of similar elements between what I'm asking you to do here and what I'm about to tell you. In that 15 minutes of Q&A, Addy and I are going to be critical of your design. Please know that like that is our job in a design review. We want to make sure that you are going to make something that will work and is going to give you lots of happiness in the future, and it's going to be something you learn from. So we're going to be critical. We're going to be pushing you all a little bit, but we're doing this because we care. We want you to have something that you enjoy making, does something cool, and that you learn a lot from. So anyway, scheduling link is going to go live after lecture, but before then, any questions? Anything that doesn't make a ton of sense? Awesome. Cool. So with that, today's plan is we're going to basically do that DR for the Bluetooth speaker. We're going to first talk about design requirements for the speaker, like what do we need it to do functionally in order to be something that's useful. And then we're going to go into the functional blocks of the circuit. You've seen a lot of these already, actually. Like when you did Lab 2, you were literally just copying stuff from our design over into your own schematic. So a lot of these functional blocks are going to be things you've seen before, primarily in the form of like schematic names and like green sheets in your top level. So again, we're going to walk through what each of those means like in some amount of detail. And we're going to talk a lot about what that means for like actually designing the PCB itself. There are some parts of the circuit where you care about some particular quality, some particular metric, and a lot of parts of the circuit where you don't even bother. So we're gonna talk about what that means, and we're gonna try and like introduce a tasteful amount of electrical engineering theory in order to convince you that like those concerns are valid and some of them are not. Cool. And then we'll just apply that to each block. We'll do a deep dive into them. And the goal of this is to basically do for track 1 people what we did for track 2 people last week when we did the deep dive on the motor controller to give you context for like how everything works and orient you. We're trying to do the same thing here. Next week, we're going to talk about like systematic debugging and how to like isolate problems and make it so you're not just crying over a circuit that doesn't work for some terribly large amount of time. And in order to know how to systematically debug stuff, you need to know how your system works. Otherwise, you're just like changing random inputs and seeing what happens. So yeah, we're gonna hopefully walk out of this today with like some knowledge of like, if my Bluetooth speaker isn't, producing sound, how do I, like, what parts of the circuit could I look at in order to try and like investigate why that's happening. And we'll talk about more general debugging next week. Cool? Any questions? Any questions? Excellent. Sweet. So let's jump into the design of the Bluetooth speaker. And as with all good design, we're going to start with design requirements. And we're going to play a similar exercise to what we did in the first lecture when we talked about what's required for like a hydrogen-powered motorcycle. We're now designing a Bluetooth speaker. What should that Bluetooth speaker be able to do? Speak, exactly. We should be able to like, well, yes. But like, can you narrow that down a little more specifically for me? Like playing audio, but how? I mean, yeah. So we have like play audio from Bluetooth, right? But many devices satisfy that criteria. Earbuds do, headphones do, and my like aunt's Toyota RAV4 all satisfy that. Please, well, we need some more specificity here. What else should this be able to do? Yeah, go ahead. Exactly, should contain a battery. Excellent. And so we have a battery in something. And again, as we talked about the Bluetooth speaker, and as we found with the BMS in lab 2, batteries are fickle devices, are they not? So what else should we put in there in order to make sure that our batteries are happy? Yeah? Okay, yes. We should make, that's an excellent design requirement. Don't explode. But what does that mean in the context of a battery? How would one explode? And what failure modes do we need to prevent? Yeah. Exactly. Prevent overdischarge and overcharge. Okay, any other failure modes that we should keep in mind? Overheating. I'm going to call that overtemperature. Excellent. Okay, we're going to have some kind of battery in there, and I'm going to throw another design requirement in here. Because we were trying to save money for this, we were scrounging around for batteries that we could obtain for like low cost. And there's a lovely world out there of low-cost batteries, and most of them will blow up and like make your day very, very sad. If you look around on eBay, you can find really sketchy stuff for like alarmingly cheap. And we didn't want to go that route and give you something that like we wouldn't be 100% confident was super safe for y'all, because giving y'all tiny little like explodey devices, it's probably a felony depending on how you define it. Yeah, and that just is like too much like hairy legal stuff. So anyway, we were able to find a set of 18650s, which are a cylindrical lithium cell. They're rather safe. We had a spare bunch of them upstairs, courtesy of Joe Steinmeier. So they're actually all from like old vape pens. As a result, like for whatever reason, the like vaping community has like a lot of research on like what on like cell testing and performance in order to get like the best possible like vaping experience or something. So surprisingly, these cells are actually like reasonably well documented and tested, courtesy of a couple people on the internet. So all that to say, we're going to use 18650s. Cool. All right. Let's go. All right, sorry about that. We're going to get out of specifics for a second. What else should our Bluetooth speaker be able to do? We have something that can play audio from Bluetooth and be portable, have some battery. Again, earbuds satisfy this. I mean, except for the 18650 part, but yeah. What do you mean by that? Exactly. We are cool people, and cool people have loudspeakers, is the fundamental thing there. After digging around a bit online, we found that like the rough way that you measure like speaker output power is with watts, which is just acoustic or electrical power coming out of or into the speaker. And we found that like for most stuff that you can buy out there, like something in the order of like 10 to 20 watts of output power is generally enough to fill like a moderate-sized room, like maybe a bedroom or something. We found this by just looking at like speakers that you can buy out there from like JBL, Bose, those kinds of people, and just checking what their output power is. So 10 to 20 watts, something in there is like reasonable. Cool. What else should it be able to do? Charge. Thank you. And what's a good way of charging a Bluetooth speaker? How do yours charge? From an outlet, but do we plug them directly into the outlet? No. Sure. How do we charge like a Bluetooth device? For my aunt's Toyota RAV4, it's a car battery with an alternator, but that's probably not what we want here. Yes? Exactly. We're just going to use regular old USB. USB is a massive protocol. It's been around for a bajillion years, and it's wonderful. There's a lot that you can do with it. You can transfer power. You can transfer data. It's delightful. However, the USB standard is arbitrated by I believe it's called the USB Implementers Forum, and they're more about chill vibes rather than implementing rigorous specs. So there's a bunch of weird stuff we have to worry about with USB, namely making sure that we don't draw too much power from it. What this effectively means is the original version of the USB standard said that you can only draw at most 500 milliamps from the USB port, and every standard since then includes the original USB standard. I think it's either 1.0 or 1.1. I forget exactly which. But basically what this means is that in order to make sure that we don't blow up any device that we plug into, we can't draw more than 500 milliamps from the charging port. We could draw, if we knew that every device we would plug into was USB 2, 3, 3.1, or a Type-C device, we could pull more power here. I've got a MacBook, and I plugged this into my flatmate's 120 watt Type-C charger last night because it was dead, and I got 30% of my battery charge back in 5 minutes. That's outstanding. However, there's a lot of circuitry happening under the hood in order to make that work. We don't want to put that complexity on you, so we're just going to say 500 milliamps of charge. Cool. I think that's about everything that everything that the speaker needs to be able to do. And here's our full list of design requirements. So you all were totally right. We're going to need to get audio over Bluetooth, and then we need to play it out over a speaker at some reasonably loud volume. It needs to be portable, and we mentioned the 18650 cells and battery safety there. The only extra design constraints that y'all did not spec on there are something that are design requirements we imposed because we wanted to add pedagogical value to the class. Namely, we wanted it to be programmable so that if y'all want to hack on the firmware, you totally can. Because this will need to include some kind of firmware, and ideally we'd like it to be changeable. So if anything weird happens, we have the option to go in and fix it. We also want it to sound pretty good because we're not going to make you put all this effort into designing something and laying it out and have you make something that you wouldn't enjoy using. We want to give you something functional. And so we actually put a decent amount of time into the testing a bunch of different chips and circuit topologies when we were designing this thing, so that we'd give you something that actually sounds good. We also wanted to be as cheap as possible because we wanted to have as many people in the class as we could. So we spent a long time engineering the value of this, so we can have the materials cost as little as we could, because the more expense that we could save on the speaker turned into more students we could have in the class. So that was part of our design process there. Cool. Whoops. OK, excellent. So y'all, we're going to jump into what exactly the design looks like. And a lot of this is going to be stuff that you've seen before. So mentally, please try not to answer these questions with the schematic names that y'all just laid out in Lab 2. But functionally, what parts do we need in order to make this device work? I hear some murmurs. Does anyone want to share with the class? Yeah.
Some kind of battery management circuitry?
Sure. Sure. So we need some kind of battery management. I'm going to just call that a BMS. But more broadly, we need to manage the battery and make sure it doesn't blow up. But what else does that battery have to do? Right, it has to charge. And what else? It's not a very useful battery if all we do is prevent it from blowing up and then put power into it, right? Sorry? Dissipate. We have to be able to provide power to the rest of the system, right? So we're just going to like do power supply. So all of this is what's encompassed inside of the power schematic inside of your like lab 2 schematics. So cool, we have that. That's like baseline requirements for our system. Like, you know, it wouldn't be a very good electrical system if it didn't have any like power going into it or didn't like have any source of energy. It wouldn't do a whole lot for us. But cool, now that we have this like boilerplate here, what else do we need to put inside of our circuit? Yes? Yes, but why? Exactly. So like, we'll have a microcontroller. I'm going to abbreviate it MCU for microcontroller unit, because we need some kind of logic. We need like, well, Bluetooth is a wireless thing, right? And so that's going to be a digital protocol that we're sending over, and we need something that can manipulate digital information. Microcontroller will do the trick for us. What else does that microcontroller need in order to be useful? How do we get data into that microcontroller? Into our audio system. How does it receive, how does our speaker get like the audio information that it needs? What technology? Yeah. Yeah. Like, sorry, it's not a trick question. It's literally just like we need a Bluetooth. We just need a Bluetooth receiver on the side. The technical term for that is called a Bluetooth modem, because we do some transmit and receive on there. So it's not purely a receiver, but for functionally, yes, we receive Bluetooth on that. Cool, so now we have our audio information living inside the microcontroller. It's sitting around as digital ones and zeros inside of the logic there. Is that useful to us in that form? I see some shaking heads. No, it's not. What else do we need? Sorry? We need a DAC. What is a DAC? Exactly. We need something to convert digital information to analog. We do this with a digital to analog converter. And we will take the output of our microcontroller, throw it into the converter, and that'll give us an analog output. Why do we care? Why do we want it to be analog? Why can't we just put digital stuff into our speaker and call it a day? Yes? Yeah. Yeah, exactly. Sound waves are analog, right? Like, at least for, well, I don't know about the music I listen to, but like most music is analog, right? It's not this pulse like 1 and 0, da, 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 like noisy garbage, right? We need to convert it into analog because that's what sound is. Sound is like a variable pressure wave that like, you know, has some analog value through time. If we put just ones and zeros directly into our speaker, well, it would just sound terrible and be useless to us. Cool. Great. So then we have our digital analog converter. Can we connect that directly up to our speaker? Guess we'll throw the speaker on here. Can we connect that directly to our speaker? No, why not? It will, yeah, exactly, it's weak. When we say that the output of this guy is weak, what we are really saying is like that it just does not have the ability to put current into the speaker. The reason why we care about that is because if you look at a speaker, take like a cross section of it, what a speaker is on the inside is this like, what's the best way to draw this? What a speaker is like a cone that's made of like some kind of like rigid plasticky kind of thing that has a coil of wire on it, and then it's floating above a magnet. North pole here, south pole here. Is that big enough? Can people see that okay? Okay, cool. Well, we're going to take a quick little trip back to elementary school science real quick and say, all right, we have a coil here and 2 leads here. When we put a current through that coil, what happens? It's on magnet, exactly. When we put current through here, we will get a north pole on one side of the coil, south pole on the other side. What happens in this configuration? I have a south pole facing a north pole. What are they going to want to do? They're going to want to attract, right? So then this will pull the diaphragm, which is on this little like flexible like mesh type stuff up here. It'll pull the diaphragm down. Excellent. What happens if we reverse the direction of the current? it'll push it, right? This south pole no longer is a south pole. It's now a north pole. The south pole moves up here. So then now these are pushing them farther apart, and this pushes the speaker cone up and down. When we push air up and down in some controlled way like this, what do we get? Sound, right? So this will produce. This is how we're gonna. This is how a speaker works, and as a result, this is why we care about the ability to drive current through this coil so much, is because a coil is fundamentally just a loop of wire that's put like super close, that's just wrapped around, right? So like that's gonna have a very low resistance. We don't necessarily care too much about the speaker coil's resistance. We care about something called its impedance, which dictates a little bit of like how it interacts with the magnetic field it produces, and also the one in the magnet down here. We're not gonna worry about that too much for now, but what matters is this is just a coil of wire. So if I was to put this on the output of my DAC, what's gonna happen? I'm just gonna short it out, right? The DAC's not gonna like that. So as a result, our signal is just gonna drop down to 0, and it's not useful. Yeah?
So is it usually the coil or the magnet that's put on the diaphragm?
The question is it the coil or the magnet that's put on the diaphragm directly? And the answer is it changes. Depending on what kind of speaker you want, what kind of frequencies you're looking at, what kind of output power. For the speakers that we're giving y'all for track 1, we put the coil on the diaphragm because this coil is going to be lighter than this magnet. This lets us have the diaphragm move faster because it just doesn't have as much inertia, right? But for larger speakers, there might be some case for putting the magnet on here instead. Does that answer your question? Sweet. This lets us get better like frequency response at like higher frequencies. So like if I was making a bass subwoofer, I might be able to get away with swapping these two. But if I'm making like a tweeter that works for like higher frequency, this is not going to want to budge at all. Like at the 15 or 20 kilohertz, that's towards the higher end of audio frequency. Cool. Okay, so all that to say, what's the missing block here? A what? Amplifier, exactly. We're just going to call it an amp. Excellent. And its job is to buff up the signal coming out of the DAC. This amplifier is going to take the signal coming in, and then its job is to drive a current, denoted I, through this coil here in a manner that's specified by the input voltage here. Does that hopefully make sense? Cool. So we're going to take a deep dive into each one of these blocks and why they do what they do. But this is like fundamentally the block diagram for our entire circuit. What does this look like after lab 2? Does it remind you of any like green blocks in a particular electronic design software? It's our top level schematic, right? Like this, what we've functionally done when we went to Altium is we had a bunch of schematics that each contain these parts of the design. And we put them together into a top level. The reason why we did this is because modularity is really, really powerful. Software people know this. And what this lets us do is if we, let's say that we were making a fleet of Bluetooth speakers. We were some company. And we wanted to like successfully make newer, better models. Well, let's say that I wanted to release a new speaker that instead of having a 10 to 20 watt output power, had a 200 watt. Well, I'd want to update the amplifier and the speaker, but since these are all blocks, I can just leave it, I can leave the microcontroller and the DAC and everything else alone, so that I only have to update this part. And I could also share this section of the design through other things that I want to make. And since this is all contained within a schematic, I know that it's good. So this actually saves us a ton of time when we go to design things, because just like it makes sense to reuse code, it makes sense to reuse hardware too. So that's why you break it up. And also, it's a lot easier to understand this way. Usually, you want your top level in your like schematics to reflect the kind of block diagram that you have going on here. Does that seem cool to people? Abstraction's a good thing. Modularity is delightful. Good kind of vibes. OK, great. Sweet. So let's go ahead and jump into this here. For whatever it's worth, the flow of information from here to here to here to here is generally called the signal path. because engineers are great at naming things with words that just reflect exactly what they are. So it is the path of signal from one place to the next. So we're going to chase the signal path. And it's going to start with Bluetooth. OK, so our design requirement is that we have something that can accept input over Bluetooth. However, a lot of Bluetooth devices do that. So we have to be a little more specific here. What kinds of Bluetooth devices can I have? We're about to design a speaker, but what other things are there? Yes. Exactly. You can have keyboards and mice. And if you're really fancy and have an Apple Pencil, we have those too. I believe those are referred to as styluses in industry parlance. What else can we have Bluetooth devices do? Wearables. Elaborate on that. Yes, we can have just like, we can have watches too, sure. Cool. What about things that Bluetooth can do that is audio, but not quite a Bluetooth speaker? Yes? What do you mean by that? Yes. That's the difference between a Bluetooth speaker, a Bluetooth headphone, and a Bluetooth earbud is fundamentally like output power, right, and size. They use a lot of the same protocols when they're playing music. But if I have a Bluetooth headphone or a Bluetooth earbud, what can it do that a speaker can't? My Ant's RAV4 can also do this. Yeah? Yes, why? Why would we want a microphone on there? Right, we want to be able to take calls and whatnot, right? In industry parlance, those are called, make sure I get the term right. Those are called headsets. Again, in industry parlance. Cool. There's also another. Yeah, that's basically it. These are all things that use Bluetooth, but they use it for different purposes. So the way that they communicate with their host devices is different. What does that mean? Well, Bluetooth is great, but we need to be more specific. And the way that we introduce that specificity is with something called a profile. And a profile is basically an operating mode that Bluetooth device can implement in order to accomplish some function. So in the case of our keyboards, mice, and styluses, those use a protocol called HID, Human Input Device. And basically, that is the common ground for every Bluetooth device that is like a keyboard or one of those devices. This is what makes it so that if you buy an iPad, or sorry, a wireless keyboard for your iPad, it'll work on your Windows laptop and also whatever other tablets you have. It's a common ground for this. It's called HID. For things like headsets, that gets its own protocol called HSP, or sorry, its own profile called HSP, which is just the headset protocol, nothing terribly crazy. And for historical reasons, because people want to put Bluetooth in cars before they want to put it in headsets, we also have HFP, which is basically the exact same thing except for cars. This is the hands-free protocol, so you can take calls without using your hands, hands-free. None of these are what we want. So instead, we're going to be using something called A2DP. And this is I believe, the advanced audio distribution profile or something like that. But basically, what that means is this is the way that we do high-quality stereo audio transfer over Bluetooth. This is what your earbuds, your speaker, your headphones, all of that use, and it's what we need to use here. How am I doing on time? Oh, God, I got to run. And it's something that we need to implement here. if you have a pair of like headphones or earbuds that you can both listen to music on and take calls from, it'll actually switch between these profiles depending on what mode you're in. So if you're listening to Spotify, you'll be on HUDP. Whenever like your mom calls you, you'll switch over to HSP, and the audio quality will change a little bit as a result. And then once you're done calling your mom, back to HUDP. Cool, so fundamentally, this is the protocol that we care about, and it's what our microcontroller needs to be able to speak. We're going to be using an ESP32 in our design here because it actually has the microcontroller and the Bluetooth modem on board. It's all one chip, and it's also super cheap and very readily available, very well documented. If I want it, there's other chips that do the same thing, but this is literally everywhere, and it's like a $2 or $3 part. So that's why we picked it. It's also very easy to solder too, as a plus. So anyway, we have that, and then the people who make the ESP32 provide a set of libraries for implementing this, and those are a little bit rough around the edges. So there's a guy by the name of Paul Schatzman who's like wrapped all that up into an easier library, and we basically use exactly that for the speaker. All that information is on our is on the site. Cool. So now we have HUDP coming into our microcontroller. We now need to get this out to the DAC, right? And the means for doing that, we will talk about after a short little 5-minute break. We'll get started back at 50. All right, we're gonna go ahead and get back started up again. What we care about next in our signal path is the digital to analog converter. And the main way that we specify digital to analog converters is we parameterize them primarily by something called the bit width. So, and that's our primary spec. Now, what does that mean? Well, fundamentally, a digital to analog converter needs to work by taking some input range. Let's say we have a voltage range from here to here. And I'm going to use the one that we have in the speaker as an example. It runs at a 0 to 3.3 volt range. That's pretty common for digital logic. And basically what we need to do here is we want to output any value along this range. But how many, but we can only give it digital bits, right? If I want to specify any arbitrary value on here, how many bits do I need in order to do that? A lot, an infinite amount, right? Because we have like, there's a uncountably infinite amount of numbers between 0 and 3.3, right? So it's impossible to like specify an exact one because we would need an infinite amount of information to do so, right? And having infinite bit width parts is not something that we can make, let alone sell, let alone put in a speaker. So we have to sacrifice a little bit. Instead, what we're going to do is we're going to narrow down our range. And we're going to say we can output some discrete amount of values. Let's say that we can output 4 values. 0, or 0, 2 values in between, or 3.3. And these are all equally spaced. I can't do the math in my head for what 3.3 over 4 and 3/4 is, but whatever. Let's say that this is our output range. How many, we have 4 choices here. How many bits of information would we need to specify which choice we want? 2. Why 2? Exactly. 2 to the 2 is 4, and we have 4 options. Excellent. If I was to put this digital analog converter in the speaker, it would sound like a potato. So how do we make this better? We add more. Excellent. So the number of bits that we have to specify how many options we have here, that's called the bit width. So what's the bit width of this device? Just blurt it out. It's a 2-bit DAC. We want something more. If the ESP itself has a DAC built in, it is 12 bits wide. Can somebody tell me how many options we get for a 12-bit DAC? Okay, yes, but what is that? 4096. Thank you. That's a good 6111 student there. You get about 4,000 values. And that's 4,000 values in here, all equally spaced. does that mean our step size is in terms of voltage between like here to here? Here we divided 0 to 3.3 into 4 sections. Now we've increased our bit width. What's the size of our step now? Here it was 3.3 over 4 was our step size. What is it now? It's not a trick question, it's okay. There we go, 3.3 over 4096. And that's like some number of millivolts. I give it to you in the lecture notes there. It's really hard to know, like from some millivolt calculation here, how good our speaker is going to sound. It's hard to look at a number and be like, yeah, that'll sound good. So the way you like fiddle with this is through testing. That's exactly what we did. I tried using ESP's like onboard DAC to drive the rest of the circuit when I was designing it, and it sounded like hot garbage. So we decided to not use the internal DAC. If we don't want an internal part, what do? Yeah, we just get another one. It's an external part. Does anyone know how wide the DAC is on what we've given y'all? If you looked at the data sheet, you'd see it. Yes. It's 32 bits. Good. Good. Does anyone know how many options we get for 32 bits? Yes, it's 2 to the 32, but what is that? About 4 billion, exactly. Now, simple question. Is 3.3 over 4096 bigger or smaller than 3.3 over 4 billion? Yes, by a lot, right? 4 billion is a much larger value than $4,000, at least according to the people who do my finances. Anyway, so that's why we use a 32-bit DAC. And that's also like a pretty like common bit width, right? Because we have 32-bit processors in our phones or a 64-bit processor. So that's actually a really nice number to pack into stuff. So that makes our jobs a little bit easier. Excellent. We now have a DAC. Splendid. This is great. This assumes that we can put some value on the DAC that is arbitrary and that we want. How do we do that? How are we going to get stuff out of the microcontroller and put it onto the DAC? Again, not a trick question. Say that a little bit louder. Cereal. What is cereal? It's not a soup. But what is it?
It's like you just give the bits sequentially.
Exactly. Well, to take one step farther back, cereal is a communication protocol. We need some way of communicating the data from our microcontroller to our DAC. And my laptop turned off. But this is the way that we do it. These are both digital systems trying to move digital data. So we use a digital interface. Digital interfaces work by having ones and zeros, and that's exactly what we see here. So this particular protocol is called I2S. If you've ever heard of something called I2C, it's not that. It's I2S. And what I2S is inter-IC sound. It's a protocol made by, I believe, Philips back in the 80s. And all it does is move audio from one digital thing to another digital thing. It's very simple, it has one purpose. But we're engineers, so we figured out a bajillion ways to make it complicated. There's a couple variations on I2S. This is the most common one, and it's the one that we are going to have our ESP and DAC talk to each other with. It works like this. We have 3 signals, and the first of which is a clock, which is a signal that the ESP is going to give the DAC in order to synchronize everything. And then we're going to say that we're going to have our logic such that whenever we see the falling edge of this clock here, that we are going to perform some operations. Or sorry, the rising edge is what I meant. We see the rising edge of the serial clock, we're going to do stuff. What stuff exactly? Well, transferring data. So inside of our 32-bit signal here, we want to transmit each bit, right? We need to make sure that each bit gets from the ESP to the DAC. And so we're going to do that by just firing them one after another. And that's exactly what we do here. So starting with the one that's what's called the least significant bit, we don't mean that personally. It's doing a great job, and we're really proud of it. But starting with the least significant bit, we go ahead and start shooting them across, starting with the MSB, most significant bit, we start shooting them across the channel. Every time we see a clock, we position the value of serial data, that line there, to reflect what bit we want to transfer. If we want to send a 0, we leave it as 0 volts. If we want to send a 1, we leave it at 3.3. And then we keep doing that on every clock. Now, this protocol sends stereo audio, meaning we have a left and right channel. So we have another signal on there to determine whether or not we're talking about the left channel or the right channel, and that's WS, word select. The reason why it's called that is because back in the olden days, or actually, never mind, still currently, we have the word used, or sorry, the word is meant to describe the amount of bits in like one chunk of information that we're trying to transfer. So here we have a 32-bit word, and so we need to select whether or not that 32-bit word goes to the left channel or the right channel. That's what that signal does. Cool. This is called I2S, and it is a digital, like we said, digital protocol, and we have test points broken out for it on your Bluetooth speakers. So if you're not getting sound out of it next week, you can check this and make sure that data is actually coming out of your ESP and into your DAC. Any questions about this thus far? Check out? Sounds good. This kind of digital communications is like the foundation of like everything in like digital electronics. If you're interested, shameless plug for 6111 or 6205, where you do this a lot. I also TA'd last semester. I'm totally not biased. Cool. So we have a digital analog converter now, and we have stuff running across with I2S. Fabulous. Okay, what's the last step in our signal chain? What's the last step in our signal chain? It's the amplifier. And this is going to work very, very similarly to the motor control stuff that we saw last week. And just as a quick review, motors are made of coils of wire, right? And they have magnets inside, and those magnets happen to be spinning. That spinning bit makes everything really complicated. However, we have a coil of wire here, and it's not spinning, it's staying straight, but it's moving up and down, right? So this is fundamentally the same problem electrically. We're trying to control current moving in and out of a coil. And so how did we do that last time with motors? What was the circuit that we used for that? We use transistors, and we use them in this kind of an arrangement, right? Where we had a pair of switches that was connected to some kind of voltage source, and we use this to program the voltage at this point, right? Depending on what the value, whether or not the switch was open or closed, right? Gentle nods, gentle nods. Okay, cool. What we're going to do here is literally the exact same thing for the amplifier. However, how many pins did our motor have? How many points do we had to control the voltage on? 3. How many does our speaker have? 2. So should this be easier or harder? Hopefully easier, good. Cautious optimism, we'll take it. Excellent, so we'll put this in here, and then we have the right side of the speaker, left side of the speaker, and then in here is the coil, and then our diaphragm. And this particular amplifier setup is called a Class D amplifier. And the history of electrical engineering for a long time has been to make newer, better, more power-efficient amplifiers. Even in the old days of telegraphy and radio, people have always been trying to make better and better amplifiers. And so this particular device is not alone in function. We could have chosen a Class A amplifier, a Class B amplifier, a Class AB amplifier. You pick the letter, there's an amplifier for you. We chose this one because of 2 reasons. The first being it's very high efficiency. Just like we talked about last time, or a week ago, motors have a very high efficiency when we drive them in the right way. So this inherits the same circuit topology fundamentally, and so we get the same efficiency wins as well. So there's that. That's a primary reason for it. The secondary reason is because it's also the same type of amplifier. This is my favorite little Bluetooth speaker. I went on YouTube and saw some dude who did a disassembly video of it in like 4K and just stole the part number off of it. And that's why it's inside y'all's design now. So thank the engineers on the like JBL Flip 4 or whatever it is for giving us the part number for this. It's not to say we didn't test it and do some looking around, but it's one of the more popular like audio amplifier chips, and it contains basically this entire circuit in one package. Cool. So basically, it works in the exact same way as we saw the motor last time. We have some conditions on the states these switches can occupy, and could anyone remind me what those are? What do we not want to do to our input? Why? And probably blow up. We're trying to avoid that. Excellent, excellent consideration. So we don't want both of these to be closed at the same time, but just like the motor, we get the choice of whether or not we put current through this way, or if we have none whatsoever, depending on our switch configuration here. And so the chip that we give you for the audio amp takes in that analog signal from the DAC, computes all of the switch timing and stuff for you, and then all you got to do is slap your speaker on it. It's actually pretty darn awesome that we can buy this kind of stuff nowadays. So that's all we got to do. The one caveat there is that, does anyone remember the technique that we used to change the amount of current going through here? I got very excited about it. There's a 3-letter acronym. Who's that? PWM, exactly. So that PWM signal, basically, we're turning our speaker on and off for varying lengths of time in order to make some kind of signal that looks like, I don't know, say something that looks like this, right? This is the voltage that's going on the speaker. And this is worth a mention because, wait a second, is this a digital or an analog signal? It's a digital signal. What did we start out with? All the way back when we got stuff off of our phones from Bluetooth. What did we start with? A digital signal. Does this seem a little concerning that we've gone like from digital to analog with a very spiffy 32-bit DAC, and then right back to digital again? It's a little bit weird. And truthfully, we could have done the whole thing without the DAC here. We could have had the microcontroller directly control these transistors and do all of that internally. However, that's really hard, and we didn't want to have you engineer that kind of like output because fundamentally that's a motor controller but without the motor. It's like it is fundamentally the same thing where we have some kind of microcontroller twiddling these switches for us in a way that we want. And instead we wanted to go with something that like was modular enough for y'all to be able to like debug well. So that was a design choice that we made so that we wouldn't have a bunch of like really weird stuff going on. I hope you're okay with that. So cool. We have some PWM going on here on the audio amplifier. And the one thing to note here is that this like kind of square wave here, can anyone tell me what this looks like in frequency space? For those that have taken 6003 or some other kind of signals class. If I was to take a Fourier transform of this, what would it look like? Yes? Yep. Yeah, exactly. If we were to take a Fourier transform of this, what that tells us is how much like frequency content there is inside of this thing. We would get a little peak here at our switching frequency, the space between here and here. So we're going to get, that's our switching frequency, we're going to get a peak there. And they're going to get a bunch of other like weird stuff out here. Fundamentally, we don't want any of this. Like, this is all super high frequency noise. We want to get out of our circuit. How do we do that? Half of electrical engineering has been devoted to making amplifiers. What's the other half been devoted to making? Filters, thank you. So what we're going to do is we're going to put in a filter that will cut off this stuff here. What kind of filter do I need? Do I want to? We need a low-pass filter. Why? Because we want to pass a low frequency and chop all this stuff off. And so in order to do this, we've chosen a filter type called a LC filter. The reason being is because it uses an inductor and a capacitor. The C is for capacitor, and the L, naturally, is for inductor. And it looks like this. We have our, our dirty input signal coming in here. And then on the output, we have our clean signal. And what happens here is the inductor will block high-frequency stuff because inductors don't like high frequency. And the capacitor will short it because, as we learned from Blahaj on Wednesday, launch, high frequency. So we're going to try and prevent anything from getting through here, and the stuff that does, we're going to short down through there. So this effectively lets us cut off all the stuff up here, meaning that what we put into our speaker is the audio data that we want. Y'all will notice that in your layout, you have 4 inductors and 4 capacitors in this kind of weird output stage on the outside. If you want to know more about why exactly those values were chosen, Texas Instruments has the documentation for you. Look up the audio amplifier on their website. You'll find all kinds of math and signal stuff for it. Yes? Oh. Go ahead.
So, the PWM goes from ground to 5 volts, right? Or plus 3 volts, or whatever we're running at.
Sure. So the question is, does the PWM go from 0 to 3 volts or 0 to 5? In this case, it goes to whatever voltage we are running the amplifier at. Here, we have chosen 12 volts. The chip itself is happy to run down at 4.5, but the speaker sounds like a potato. So we didn't do that. The chip also gets really, really hot if you run it at 18 volts, and it can handle up to 20. We did some testing and found that 12 volts is a good balance of minimizing weird losses that we get in here, and also sounding reasonable. So we've chosen 12 volts. Does that sound okay?
Yeah, so I think there also needs to be an offset then for the 4080 composition.
Yes, there is. The caveat with this is that we actually, you're right that there is an offset. We do some weird stuff with the switching here, and we apply a differential signal to this. So if we want to put let's say we want to put 2 volts on the speaker, and we have 12 over here, what I can do is I can put 5 volts average on the speaker over here, and then I put 7 volts average on it over here. So the speaker sees a difference of 2 volts, but fundamentally we still have 2 voltages here that are referenced to the ground here, if that makes sense. Yeah.
The other thing was that, wouldn't it be that you want the offset for in terms of filtering, you would want to keep the offset, but you wouldn't want to have that high peak reach of the switching frequency?
Yes. So the question is, do you want to keep the offset that we've introduced here and just cut off the high-pitched squeaking? And the answer is yes. That offset that you're referring to has 0 frequency associated to it, just a constant value. That'll pass right on through this whole thing. So the inductor looks like a short to things at DC, but once we start varying our voltage and we start applying AC, that's when it starts resisting stuff. And just with the capacitor, when we apply DC to it, it's totally happy, but as soon as we start applying AC, that shark is going to go munch, and short it all to ground. Sound good?
Yeah.
All right, sweet. Yeah, what's up?
Why not use a switching frequency that is just above human hearing?
Galaxy brain maneuver. We just have a switching frequency that's above human hearing. Yes, we do. This particular amplifier switches at 500 something kilohertz. There's actually some settings on it to tell it to steer itself away from the AM radio bands, because we actually are interfering with those frequencies a little bit. So we're switching at many hundreds of kilohertz. And even then, like, we still have these output filters because radiating that much high frequency noise into the rest of the circuit is also just a bad idea in general. So we do that partially for audio quality, partially for peace of mind. Cool, yeah.
Is there a reason that you selected an inductor and a capacitor rather than two capacitors and like some sort of other topology that just the inductor is usually pretty beefy on the board?
Yes, it is very beefy. The question is, why did we pick this kind of output topology instead of something else? There's two reasons. The first being, it is simple. It's two parts. And there's also, it's two parts, and these are actually like pretty darn good. If you've taken 6002 and you know what a Bode plot is, I believe, correct me if I'm wrong, but this has a like filtering ability of 20 dB per decade, roughly, minus 20 dB per decade, which is actually pretty darn good. We could do better by introducing, like, we could have bigger parts here that would filter better, or we could have a different filter topology that lets us be more selective. But this is good enough for what we want. Mostly because our harmonics are super high up here, because our base frequency is like 500 kilohertz or so. So these harmonics are actually spaced really far apart. So by the time we actually run into a harmonic, our filtering is very strong, if that makes sense. Yes?
Real quick addition. Other topologies you might have seen in these kind of filters are like RC filters or RLC filters that use a resistor on the output. The reason we don't want to use a resistor is because we have just spent a whole bunch of energy amplifying our signal, and then when you run it through a resistor, it de-amplifies the signal. So then you would need an amplifier on the out. It's just a chicken and egg continuous resistor amplifier, resistor amplifier, resistor amplifier to get the signal you kind of want.
Mm-hmm.
And then the reason you probably wouldn't use a capacitor is kind of what we were talking about in lecture on Wednesday, because if you use a capacitor, you would need multiple, like, you would need many capacitors to filter out all the kind of, so to do it effectively, like if you really want a proper negative 20 dB cutoff, like a full cutoff of your signal, the roll-off a capacitor has a 20 dB cutoff range is very narrow. So every single signal or frequency that you want to filter would need its own individual capacitor, whereas the inductor will roll off all those frequencies at a much sharper rate.
Yep. Just to like tack on to what Addy said too, for an RC filter or an RL filter, I believe those are only like minus 10 dB per decade. So it's like only half as good too. It's half as good, doesn't burn a lot of, and it burns a lot of power. So, okay, cool. What's the only other part left on here that we haven't talked about yet? Got through the amplifier, power, right? The power circuitry is a little bit of a exercise in bookkeeping. We have a part that is literally just a battery charger that we put on there, and it's just one part that takes care of everything. It prevents it from charging too much, and it will has like a little status LED on there too that like lights up when we're done charging and stuff like that. So that exists. That's literally just a part that we got from Microchip. It's like an MCP 7300 something. Cool. That takes care of preventing overcharge. How do we want to take care of preventing undercharge? Well, that's a little bit of a harder problem because we need to turn everything here off when we get to too low of a battery voltage. The way that we do that is a little nuanced. I put that in the lecture notes for today. I'll ask you to, like, if you're curious, go take a look at that. But basically, we're relying on the ESP, the microcontroller, turning off before everything else does. And this has a control signal on it such that when the microcontroller goes down, it takes everything else with it. Cool. So that takes care of overcharge, overcharging, over-discharging. We also have power supplies on board. There's a 12-volt one for the amplifier here that uses something called a boost converter. And again, those are common enough to the point where like explanations for those are plentiful out there, and you've probably seen them before. So I'll leave that as an exercise. Cool. That's the power circuitry. And I want to like take the last little bit of time to talk about what all this means for layout. So fundamentally, like working our way over here, we have a Bluetooth modem next to a microcontroller. Those are both digital systems, but this Bluetooth device here, that's a radio, right? And so its job is to like radiate electromagnetic field and receive it and manage that there. So a lot of what goes into making sure the Bluetooth part of this is happy is making sure that the radio is happy and that the antenna is good and in a place that we want. Espressif, the people who make the ESP32, have done an excellent job telling you what they want. And we've linked that to you in the Lab 4 handout. They have a whole design guide on how you put this on the board so that you actually get good Bluetooth and Wi-Fi performance. So read that, they'll tell you. For the microcontroller here, all of that is mostly integrated into one module, but there's some stuff that isn't. Namely, there's a little programming interface that sits on the side here. Again, that's not part of the core functionality here, but it's explained in the notes. So if you're curious about that, have a read through. So we have a programming interface that's digital, and then we also have the DAC coming out here that's digital. And that's important because in our design here, we have both digital and analog signals, right? Which one do you think is going to be more susceptible to noise? There's some murmurs of it, a little bit louder. Analog is going to be way more susceptible to noise, right? So what we want to do is these traces that are going between the microcontroller and DAC, you have to pick where those go. They're carrying I2S. You have to pick where they go. So these are going to be less sensitive to noise. So given the choice, would you want to make these longer or shorter than the analog stuff out here when it comes to board layout? Longer? Longer. Because it's okay if there's a little bit of interference over here, but we want to keep this as tight as possible. This is a rule that we didn't respect to the letter when we made our layout. We could have moved some blocks around such that the analog signal circuitry was a little bit closer, but it works well enough for what we've got going on here. Cool. That's worth keeping in mind. We also have just one last comment on the digital side. We're charging this over USB, but we're also going to program it over USB. USB has 2 signals in it called D+ and D-. And what's special about them? You did this when you were laying out schematics. You had to tell Altium about it with a little red marker. It's a differential pair, right? And that exists for all the reasons that Adi talked about earlier in the week. But there's a differential pair here. And we have to respect that and route it as such. So we're going to keep that in mind. Cool. Moving on to the DAC, half of it is digital, half of it's analog. So this is an excellent point to start thinking about the separation of digital and analog. So everything over here could be whatever. We make sure the radio is happy, and we can kind of route it however we'd like. But once we start going over here, we got to be really careful about making things tight. And especially once we get out of the amplifier and going to the speaker, what are these signals here? Those are our speaker currents, right? Are those going to be high currents? They're going to be large? They're going to be tiny? They're going to be large, right? So as we were talking about before, Adi mentioned this, but if I have a large current that's going out to a speaker and coming all the way back to my board, what is this? It's an inductive loop. And this is going to make some amount of B field. And right-hand rule comes through this way, so we're going to have all kinds of magnetic field coming into the chalkboard here. This is bad for EMI, and so when you're making speaker enclosures, you really want to keep these leads as short as possible. And we're going to believe in that philosophy when we lay out the PCB. These traces here, we want to keep them short and want to keep them thick, so that we have as little resistance as possible between here and here. And then when we make the enclosure, we want to keep those nice and juicy as well. Juicy and short. Cool. There's also some other considerations inside the amplifier. Thus far, we've only been talking about electrical stuff for the amplifier. What else is there? We're converting stuff from our battery, or sorry, our 12-volt rail, the boost converter is making, putting it in a signal out here. Is that free? Heat, exactly. This amplifier is going to make some heat. It's a Class D amp, so we have efficiency in the 90%-ish range, but it's still going to make some. We got to do something about it. So when you go to lay this thing out, you will notice in the TI documentation that they want you to put they want you to lay out your chip on a board like this. Here's our chip. Here's the leads coming off, which you now know how to solder. Nice job on Lab 3, by the way. Y'all impressed me a lot with the ability to do the small parts. What they're going to want you to do is put vias underneath it, because these are like little filled pieces of copper that are going to take all the heat and wick it away from the part. There's an exposed metal pad on the bottom of this that will be soldered to, and this is going to pull heat out of the device into the board and dissipate it. These are called thermal vias. You might have mentioned them before. Think about them when you're routing stuff. We did not put these on the board because, truthfully, I was routing it at like 4 in the morning. I just completely spaced that part of the application bit. But we're going to want to see this in y'all's designs. So keep that in mind. Cool. So we see that inside the amplifier, and then we go out to the speaker, and then the rest is up to the mechanical design of our enclosure. Cool. You're going to want to. One other thing to mention here is that we have fundamentally, or one more thing to mention before we wrap up. There's fundamentally 3 domains on this board. That's part of the reason why we asked you to design it. We have the digital domain, the analog domain, and then can anyone guess what the third one is? Yes, exactly. Digital, analog, and power. What happens in our power circuitry that we might care a lot about in order to separate it from our digital and analog sides? We're providing power, right? Power, well, we need voltage. Well, power is voltage times current. We're getting voltage from the battery, but we got a lot of current flying around, right? What's the issue with current flying around on our board? Oh, wrong board. Where'd it go? Oh, it's right here, sorry. Same problem here, right? Like we have this, we are radiating a ton of field from all of our power converters and stuff, and we really don't like that. So this gets its own like kind of class of existence because it has a lot of pulsed currents because that's the way the boost converter works. I'm not going to go into that because it's, I'm going to ask you to take it a priori, and we don't have a ton of time for it. So anyway, there's 3 basic like domains here. Power, we care about thermals and like switching currents. Digital, we care about having signals that are robust and communicate what we want. And in analog, we care a lot about having signals that are free from noise and carry the information that we want, and we protect them. Cool. Part of the reason why we asked you to make a Bluetooth speaker was because that was one of the only things that we could think of that was that contained all 3 of these domains that you have to think about when you're doing layout, and also did something cool and useful that you would like and be like, I don't know, a fun thing to have. If you have ideas for other systems that contain these for future runnings of this course, please let us know. I'm very curious to hear your thoughts. So anyway, all that to say, these are our big domains. Sometimes hear them called routing domains. And just keep in mind that like you probably want your power stuff away from your analog stuff, away from your digital stuff. And you'll see that respected a little bit on the boards that you'll be populating on Tuesday. Cool. All right, that basically takes us to time. Any questions before we wrap up? Okay, excellent. I'm going to take blank stares as this all made perfect sense. You loved it. You loved every minute of it. And in that case, we will see you on Monday. Have a lovely weekend, everyone.